morning. So I'm going to talk in the next half hour about global markets. So I'm going to give a quick overview of the environment. I'll go into some of the market results, both revenue and units. I'll look at some of the applications for PIC platforms and a little bit of roadmap analysis so that we can tee ourselves up for the rest of this week. And then I'll do some closing remarks. One of the big things in my view graphs are these green bars at the bottom. So if the data is too complicated or it's too small or you can't see it from the back, the green bar is sort of the takeaway. It gives you the sort of the one-liner. So an introduction and a memory challenge. 3 takeaways to remember today. Photonics enables many things and is already part of our lifestyle. We'll see a lot more about that. Photonics will be integrated just like ICs 50 years ago and will drive new product designs and markets. And the last part is integrated photonics a paradigm shift for the tech community? So our thirst for smaller, lighter, faster will enable PICs, photonic integrated circuits. So a quick review of the environment. Well, I actually went back 140 years, Professor Bell with his photophone, and it's really interesting. What is a photophone? It's really the conveyance of video data. In this particular case, in 1880, he was talking about sunbeams, which is not, it's still doing light, but it's not actually fiber optics. But was he lucky or visionary, perhaps even clairvoyant? Well, if you think about 1880 and you look at the latest data today from the IP traffic, we're in terms of 100 exabytes per month. And you start to think about what's an exabyte. So to make it easier, and you can see that what I've ringed at the top there is video. Video is 67% of that bar. It's the dark blue bar. So most of the data going across the internet is video. And on the right-hand side, well, remember the old telephone at 6 kilobits per second. And then you've got your megabits per second for home internet, and you've got your data centers looking at gigabits per second. Front plates on switches are now looking at terabits per second. Traffic is petabits. Traffic today, exabytes. And then traffic tomorrow, zettabyte. But actually, if you really think about that graph on the top left, it's 100 exabytes per month. So if you multiply that by 12, we're actually into the 1 zettabyte of traffic going across the internet, and that's only increasing. So it's a complicated little scale, but it just gives you some idea that 140 years ago, this Professor Bell actually was probably correct. So with that, let's look at some of the data center needs. What I've tried to do in this slide is try and summarize some of the challenges that the data center folks actually have and they need to solve. You can see larger, faster, denser, greener, and economic. And through some of the solutions we're looking at, integrated photonics can actually get these guys there in the data center. And what I've written at the bottom there is a scalable photonic integrated circuit, a scalable PIC platform will win that data center market. And looking at those 5 metrics, the first one is larger. We're now beginning to see a lot more single mode fiber being used in the data centers. Now, some data centers are still using copper and some still using multimode fiber. But you look at the latest strategy from Facebook, and they're talking about single mode fiber everywhere. So some of their architectures actually are looking to eliminate some of the classic incumbent technologies. And 100 and 400 gigabits per second becomes more ubiquitous using single mode fiber. So we're seeing a lot of that today. This is a graph from the Ethernet Alliance. The battle for the data center will be at 400 gigabits per second. We're beginning to see that occur in the major conferences and the major work today. And you look at this, and I've drawn some cross swords at 400G. But if you look at that roadmap, you can see the roadmap looks out beyond 400G to 1 terabit. So as technologists trying to put a roadmap together, we've got to think how that's all going to work in the future. In terms of denser, I mean, classic laser packages are shown here on the bottom left-hand side. And we're going to silicon-like platforms on the top right-hand side. So we're actually using integrated technology, PIC platforms. We're using wafer scale manufacturing. We're using flip chip technologies. We're using 3D silicon design, chip on board, silicon optical bench. We're using these technologies today. We're going to see more of these technologies in the future. Using silicon-like platform enables the scale-in. And in fact, if you look at the face plates of the switches within the data center today, I've just picked an example. This example here is 0.6 terabits per second. What does that really mean? So if you look at the top line there, if you have 22 QSFP28, which are 100 gigabit transceivers, you have 22 of those, you have 2.2 terabits per second. And the customers are requesting 50 to 100. So that's a little bit of a challenge. So if you've got 22, and this one at the bottom is only showing 0.6, so that's like 5-6 times faster than this one I'm showing. How do you do that? I mean, it's actually a physical challenge. It's not just a transceiver challenge. It's how do you get all that data through that front panel? And integrated photonics has the potential to get there, but what does it actually look like? In fact, on the next slide, I talked to the guys at Google who are designing the new next generation data centers, and this is one of the graphs that they're using. And they're talking about bandwidth density. That's how much bandwidth you can get through that faceplate on the switch. And that's that dark black line. So that's this one here. And you can see that's increasing about a decade every 7 years. And the problem they're having at Google is that you look at the switch capacity growth, which is how much traffic that's going through, and that's actually growing faster. So you've got that pink line here. And they're actually talking about modules that are 400G, they're calling it the octal SFP, but they're also looking at the 800. So they're already thinking about that already in their architectures. And so we have a gap appearing. The gap appearing is that switch capacity is growing actually faster than what the bandwidth density is going to be able to handle. So that, as engineers and technologists, that's a huge challenge for us to go figure out that problem. How do we make it easier for these guys to implement that increasing traffic? And so the concern, as you can see, the takeaway here is that pluggable optics needs to scale faster at 400 gigabits plus. That's a huge challenge for us. It's also really exciting too. And in fact, if you look at some of the trends is we've gone from big transceiver boxes, CFP, down to small transceiver boxes. And in fact, some of the new faceplate designs have these like green spots. These green spots are cross sections of fibers. So now folks are actually thinking about not just having, ports in the front, but actually taking fibers through the faceplate and having connections right onto the board, because it's actually becoming an issue. And I think I've shown this conceptually here is the onboard optics, taking fibers all the way through and actually collecting the fibers to the printed circuit board, and actually saves room at the front. But also, as you can see from the top of this slide, I mean, these data centers have to be greener, so we have to think about lower power. So we have to figure out how to get the power down in some of these transceivers. Smaller certainly drives lower power, and if you look at some of the latest data from Google, you can see that it's actually decreasing a decade every 10 years. So the energy per bit in terms of picojoules is actually going down. These are sort of orangey spots are the 100 gigabits per second transceivers. But the takeaway from this slide is the thermal management is critical to address, because we're generating a lot more heat, and we have to figure out how to get the heat out. And so that's going to become a problem. In terms of economic designs, the metric of $1 per gigabit at 400 gigabits per second comes up time and time again. And this is the same graph. It's plotted linear at the top and log at the bottom. And you can see, as you look at 100G and 400G transceivers, there is a potential we can actually achieve this metric. It's not impossible. It just needs really good, innovative manufacturing design. Integrated photonics, from at least my perspective, is the key to achieve these economies of scale and meet the metrics the customers are looking for. So global markets, let's take a look at the global markets. The global market in terms of everything, in terms of photonic components, that's in the datacom as well as the telecom markets, turns out to be about, I think it's 17, what's the number in 2017? There we go, $21 billion in 2017, rising to $43 billion by 2025. So there's strong growth forecasted in photonics components in both discretes and PICs. If you split that into three main segments, you've got wide area networks, you've got access, and you've got datacom. So you see the three major segments driving this number. The interesting thing is when you start looking at which of these technologies are going to be PIC-based. So in terms of trying to generate this number here, I went through all the different categories of optical components in datacom and telecom and looked at which were integrated photonics today, and you can see the number's fairly low. I think this is about 25%. But the surprising thing is that by 2025, about 70% of the photonic components are actually going to be integrated in some form or another. That, to me, is really exciting. There's probably a fair error bar on this number, but even if that's plus or minus 10% or plus or minus 15%, that's still a huge number. And the trend is that we're going to integrated solutions. So out of the $43 billion, $30 billion of it is going to be integrated. So it will become de facto by 2025. And in fact, if you look at it just from the transceivers standpoint, so this is just transceivers in datacom and telecom, both client side and line side, you can see about 58% of that $43 billion, which is $25 billion, is going to be transceivers. So transceivers are going to play a huge role in datacom and telecom fiber communications going forward. The interesting thing, if you start to split the transceiver market down, you see it split into three main segments. You've got this dark blue area here, which is Ethernet datacom. You've got the green area here, which is wide area network client side, and you've got this blue area here, which is DWDM. So you can see where the growth is being driven from, mostly from the client side, but some on the line side. What's more interesting is you say, out of these transceivers, which are the technologies inside the transceivers, which ones are going to be photonic integration? Well, it's about 80%, it's about $20 billion, and the crossover point is around about 2021, where PICs actually are more popular than discrete technologies. So we're seeing that trend. Now, this may be 2021, 2022, but it's going to be around about this point. You're going to see integrated photonics actually become the dominant player in transceivers. This is really exciting. And if you break that segment down to see where that's really being driven from, you can see again that's Ethernet datacom in a dark blue. You can see wide area networks client side, and you can see DWDM. So you've got those similar trends in those market segments that are going to grow very quickly over the next decade. If you take a look at Ethernet and you say, okay, so which sort of data rates are really going to drive this technology, you can see some interesting facts emerge. This blue color, it means 100G is really going to be the next node. It's really going to be the main driver. Now, we do know that the 10 gigabit was the previous node, and before that it was 1 gigabit, and before that it was 100 megabits. But going forward, 100G is not going to go away very fast. It's going to be the next major node for networks. And after that, it's going to be the 400, which is this dark blue segment here. So the 100G is going to be close to $5 billion by 2025, and the 400G is going to grow quickly to $1 billion by 2025. So that just gives you some idea what the networks are thinking. The main driver for the 100G is going to be PIC-based technologies. And so in terms of, for this talk, I wanted to give some volumes to try and see how many units we're talking about. In terms of the global market, and you add up all the units in both datacom and telecom, and clearly there's more in datacom than there is in telecom, it's about 420 million units. So strong growth volume forecast in photonic components. If you break that down, you can see most of those units are going to be in wide area networks. You're going to see datacom next, and then you can see access. So the three main segments again. And if you take the top 10 segments in volume across all of data, you can see some interesting trends. So this is about 87% of all the volume of the units. But you can see these big segments. WAN actually plays heavily. This green one here is datacom receivers play heavily. Datacom Ethernet plays heavily in terms of volume, because you know a lot of these components, I mean, the lower price, the lower cost is going to be on the datacom client side of the markets. If you look at transceivers themselves, there's going to be about 100 million transceivers by 2025. So that's a lot of transceivers. That's a lot of production lines. That's a lot of growth, because we're running about 66 today. If you look at the breakdown of the transceivers, you can see the biggest part of the transceivers is actually in Ethernet, which is Ethernet datacom, which is 43 million units. There's 31 million units actually in radio and RF, which is the 3, 6, and 10 gigahertz type transceiver modules, which are actually in the network that are supporting all the mobile systems. They're not very expensive, so you're seeing a large volume of that. In terms of Ethernet, because folks are interested in where Ethernet's going in 100G and 400G, you can see very clearly this light blue line, 13 million units growing very, very quickly for 100 gigabit Ethernet. The 400 is at the bottom, it's just beginning. So the volume in terms of Ethernet is going to be driven by 10 gigabit, which is already out there into the network, which is already a node, and also 100 gigabit, which is growing very, very quickly, and the 400G, which is just emerging. In terms of looking at the telecom side of it, now the numbers are a lot lower because we know in telecom the prices are higher, the volumes are lower. And you can see line-side modules, 37 million units total. There's about 5 million units today, so there's some pretty good growth here. Some of the segments here, the MUX, DMUX, the ROADMs, amplifiers, interleavers, CAT amplifiers, etc. So there's a lot of segments put together. But the interesting thing here is the biggest segment in the line-side modules actually is this olive green color, which is MUX, DMUX, and Datacom, which is indicative of having WDMs, MUXs and DMUXs within the transceivers. And so you're going to see that growth happen very, very quickly. Because if you think about it for a second, when you talk about 100G, you're talking about 4 channels at 25, so you need to MUX and DMUX the 4 channels. If you're talking about 400G, people are talking about 4 channels or 8 channels or 16 channels. And so this little component is really going to take off over the next decade. In terms of PIC platforms, this is sort of one overview slide. It gives an idea. On the right-hand side, we have the all silicon photonic solutions. And everybody knows that we don't have a silicon laser, but it can do pretty much everything else. And that's becoming very popular, including semi-custom and custom ASICs, so you have the electronics on board. On the left-hand side of the slide, you have the all-indium phosphide, which is the incumbent, is the technology that's been around for 25 years. And you can see you can do pretty much everything other than, a big electronic chip, call it a semi-custom ASIC or a DSP. And in the middle, you've got some interesting new technologies emerging, dielectric photonics, polymer photonics, which actually can work with both sides of the equation. And so in this case, it's mostly passive technology, but it's technology that actually can operate very, very quickly, can be athermal, can be super high speed. So you're going to see, I think, combinations of all these technologies, especially used in applications like data centers. So the challenges of PICs, and this is a slide I put together about 2 months ago. How do you beat customer expectations? How do you get to this $1 per gigabit? Now, we understand the markets are growing, but we've got to actually get the cost structure correct so we can actually access those markets. Now, this is the same graph. It's on a linear scale on the left, and it's on a log scale on the right. On the linear scale, it looks, well, dollars per gigabit fall pretty quickly. We're sort of getting below $10 per gigabit, but all the lines are really condensed together. So if you look at it from a log graph, you see actually there's a gap appearing. This is your customer expectation. By 2019, 2020, they were looking at $1 per gigabit. And are we there? Well, we're not even really close. We're sort of, the best we can predict is getting sort of to $5 per gigabit. Maybe we can get a little bit lower. But in general, the industry is sort of lagging some of the expectations of, and I'm talking about customers of the large data centers, the Microsofts, the Facebooks, the Amazons, the Googles of this world. They're looking for these types of metrics. And how do you do this? Well, I think we're going to have some innovation. The innovation means we're going to have to put some roadmaps together to really chart how we're going to go from these sort of numbers, $5, $10 per gigabit, down to $1. It can be done, but we're going to have to really think carefully how to do that. So road mapping customer expectations. The next 2 or 3 slides, I did some work for USC about 3 years ago to try and put a roadmap together. And this is what we did. And it's very detailed. I don't expect anybody to read this. You can sort of look at it afterwards. But the 2015 roadmap focused on areas that needed attention. And it was very clear then that we needed PIC technology to move forward. And since then, we have AIM Photonics really taking up the baton in the States and really driving this technology. So I'm actually pleased to be part of that group now. But this roadmap did some interesting metrics. I'll go through it very quickly. if you look at the very top, what we said back then was, 2018, 2019, yeah, we're looking at 400 gigabits per second. The data rate density on the faceplates would be 100 terabits per second, so we were really sort of bullish at that time. We're going to have really small modules. Well, let's take a quick look at what we said and where we were wrong. We were right in terms of 400 gigabits by 2019. I think you're going to see 400 gigabit transceivers in the next 2 years. I saw prototypes in OFC conference just a couple of months ago. But the data rate density, 100 terabits per second on a front plate, we're only running about 3 to 5 today maximum. And that's a difficult problem. So that's actually been delayed 3 to 5 years. In terms of form factor, which is the size of the transceivers, yeah, we're not below a QSFP yet. So we're actually running behind that too. So although three years ago we were predicting these things, actually, it's actually been difficult to keep up with the metrics. And so we're now delayed 2 to 5 years. In fact, if you look at the distances for a transceiver, we said, 2 kilometers, that's about right. 2 kilometers is still apropos. Industry wish, $1 per gigabit, 2018, that's probably delayed 3 to 5 years. We're not going to get there yet. The technology plan, nobody has achieved $1 per gigabit in the industry in 2017, and it's not likely in 2018. We need some innovation, we need some roadmap, and we actually need some focus. So the technology plan has been delayed. If you look at the super short links, the very short links, these are the ones going into the computer systems, the high HPC, the high performance computer systems. Those guys, when I talked to them in 2014 and 15, they wanted 25 cents per gigabit. Yeah, so that's a quarter of a dollar, right? So have we actually achieved that? Well, there's still 125-meter links. They're using copper and multimode fiber today, so that's okay. Well, the industry wish, what's the closest we've got? Well, I said it's delayed. The closest we've got is AOC at $60, working 100 gigabits per second. That turns out to be about 2.4 gigabits per second, so we're not quite there yet. So we still got an order of magnitude out, even with the low-cost multimode links that we have today. And the technology plan, nobody's achieved even $0.50 per gigabit in 2017, and it's probably not likely by 2020. So the metrics have been delayed a little bit. And in fact, what I've done here is put a straw man roadmap, which for this conference, so we can take a look at some of these numbers. We have the purple brick wall, which is a bit like the red brick wall. It's a technology cost barrier. So in photonics, we may have the technology solution, but it's certainly not at the right cost. And so that's why we colored it purple. That's been moved out 2 to 3 years. The $1 per gigabit's been moved out 2 to 3 years, and a $0.25 per gigabit's been moved out 2 to 3 years. So everything's been delayed, which means we really do need a roadmap now that everybody has to focus on. And so I looked at some of the technologies going into this, and I listed 5 main technologies that are important for photonic integration. You've got indium phosphide, you've got silicon photonics, you've got polymers, you've got dielectric materials like triplex, and you've got gallium arsenide. And this week, hopefully, we can go through some of these numbers. And if you put the whole thing together, you see everything's delayed 2 to 3 years. So at least from my perspective, talking to some of the big data center type customers in California, there's been some delays. So the new PIC markets, it's not just, if we can do this and get close to this on the roadmap, we'll actually enable PICs to go into non-communication markets. So there's a whole bunch of different markets listed on this slide. So there's many applications, LiDAR, free space, lasercom, biophotonic sensors. We can see that here. The trend is miniaturization and low power. If we can do this in datacom and telecom, then applications like optical coherence tomography can really benefit. Today, it's discrete optical parts. We can integrate those in a chip. We can use an integrated platform. We can make these solutions handheld and battery-powered, and the customer's going to be very happy. The same thing goes for cytometry and detection. We have these big units today that are 3 meters by 3 meters by 3 meters, and we can actually make them handheld using image sensors. So these types of technologies will actually impact non-communications markets to a great way. And the same thing goes with spectroscopy. Integration enables miniaturization, infrared wavelength PICs, using discrete components today, and now we can integrate them. This is really exciting. Capsule endoscopy using photonics. This is the little pill that you swallow that has a camera in and an image sensor, and it sends out signals. I mean, these are going to have a lot more intelligence in the future, and they'll be able to do a lot more things. And you're going to see not just biophotonics, you're going to see applications in defense, medical. There's broad opportunities for photonics outside of communications. Even display concepts. Now, I'm just showing a slide here that shows organic LEDs, but you can sort of imagine some integration of photonics actually enabling some different opportunities in this sort of space. So some closing thoughts. 5 capable technology platforms. We've got indium phosphide, we've got gallium arsenide as incumbents. They've been around a long time. We've got some new challenges. We've got silicon photonics, especially for road mapping. I mean, I think that's really important. There's a lot of investment gone into this area. And there's various ways you can do that using heterogeneous techniques, oxide techniques, silicon germanium techniques. We've got newer challenges for dielectrics and polymers. But I think all will be symbiotic with each other, because in silicon photonics, we still need an indium phosphide laser. And so you're going to see different technologies work with different solutions. We all have to work together. In terms of a summary checklist here, so we know the internet's growing quickly. Video usage, new market applications are being enabled through miniaturization. We've got markets that are now looking pretty strong. They're in sort of tens of billions of dollars. We've got lots of PIC penetration. We've seen a lot of PIC penetration in transceivers. This is all really exciting. Driven by client-side DWDM data rates of 100G going to 400 gigabits per second. The market demand for PICs will certainly increase. The trend to integrate electronics and photonics for smaller real estate is now becoming extremely important. Using these base technologies to do that, and I believe PICs are the answer to get to $1 per gigabit metrics that the customer is looking for. So they will drive the next generation IC. And then the memory challenges is, we said this, photonics enables many things as part of our lifestyle. Absolutely, from fiber communication markets to non-communication markets like consumer, health, bio, defense, etc. You're going to see that happen. Will photonics be integrated like ICs? Absolutely. And it's going to be the next generation IC. Is integrated photonics a paradigm shift for the tech community? Yes, and it's becoming a major market accelerant. This is really exciting. And then the last slide is, well, I think this guy was pretty right. I mean, his photophone market is actually becoming big business today. And I'll end on that. Thank you.